keep talking about elements of a circuit, taking some of the available energy and quote unquote using it up. But where does it actually go? It can't just disappear. We know conservation of energy is the thing, so you can't create it or destroy it. That means it's getting taken out of this circuit somehow. Where is it going? So as you have a charge carrier moving around your circuit, there are certain drops in potential across each element. So V gets a little bit smaller after each element in a circuit. And in a certain time t, it loses a total amount of potential energy Q times V. Remember, that is an equation from our last unit. So the power, or the rate that it's losing energy, is going to be, whoa, how did that happen? So the rate that it's losing energy, seriously? I just want to add some text. Okay, apparently for some reason that was too high on the page to be able to add text. So anyway, the amount of energy used up is equal to Q times V. So if it's a rate, that means we just divide it by time. So the power is just Q times V divided by. But if we look at what we have here, charge times potential difference divided by time, we already learned that charge divided by time is something different. That's our current. So we can replace Q divided by T with I to say that power equals I times V. So everything that you know about power still applies here. Power is how much energy is transferred in a certain amount of time, and we called that in mechanics the watt, or W. And it totally breaks my heart that I can't do my little unit of power is the watt spiel, but I guess there's always college prep for that. And you know from last year that 1 watt, since it measures a transfer of energy over time, 1 watt is equal to 1 joule being transferred every second. For AP Physics, I'm sure you guys are pretty good with algebra and rearranging 3-variable equations, but there's a little trick if you ever feel stuck, which we might have bigger problems if that's the case. You can set up triangles. So depending on which variable you want to solve for, you have v equals I times r, I equals v divided by r equals v over I, and it works the same way for p, I, and v. So depending on what you want to solve for, you have some different equations to use. Unfortunately, it won't always be the case that you know I and V when you're trying to find a power. You might know something about the resistance, but we can take Ohm's law and make a few substitutions into our power equation to get different expressions to talk about power in terms of some object's resistance. So power, we know that P is I times V. That's what we got on the last page. But let's say we don't know what I is. We don't know the current. So we take Ohm's law, rearrange it so that it says I equals V divided by R. And then we take that and plug it in for I. So it would be V times V divided by R, or just V squared divided by R. So that's one substitution. I'll try to bold these ones so we can see which ones are really important here. Alright, so that's what we would use if we don't know anything about the current. But what if we don't know anything about the potential difference? Then we have to try and replace V. So V, we know as I times R. If we take that and plug it back in here, we would have I times R, or just I squared times R. And that's going to be another bold one, another important one for us. So we have these three different things. P equals I times V, V squared divided by R, and I squared times R. So three different ways we can find power, depending on what information we already know. How quickly energy is being transferred now, we can figure out the power, but where's it actually going? It all gets turned into heat. I don't know if you guys have ever felt your laptops, if you've been running them for a while, they tend to get kind of hot on the bottom, and that's because of all the resistance in all the different circuit components that make up your computer. So some amount of energy, depending on how much resistance there is, gets taken out in the form of heat. And I know in thermal we use Q for heat, and I really wish there would be a little bit more consistency here, but here we're going to use H for heat. If you use Q, it's really no big deal. I'll know what you're talking about. It's probably just because we use Q for charges now. So if you have Q equals Q blah 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 blah, it would just get kind of ugly. So maybe that's why they made the substitution for H. Anyway, H, the amount of heat given off, is just going to be the power times some amount of time. And then we have all these different expressions for power up above. We could say that it's IVT. We could say that it's V squared T divided by R. And we could say that it's I squared RT. So what we're really doing here is multiplying by the time to cancel out the time unit in the power. So we'll be left over essentially with some amount of energy that is being used up by a certain resistor. So a resistor is going to heat up more if you have a high current through a strong resistor over a long period of time. I guess I'd be looking at this last one here. Alright, example time. We have a circuit with a potential difference of 10 volts hooked up to a light bulb whose resistance is 20 ohms. The filament in the light bulb heats up, producing light. If the light bulb is left on for 1 minute, how much heat is produced? Alright, let's take a look at what information we have here. We know we have a potential difference of 10 volts. We have a resistance of 20 ohms. And let's see, we know that this is running for 1 minute or 60 seconds. Alright, and we want to figure out what is the heat produced. Alright, so we have a VR and a T. Let's look at our different H equations and see if there's one that would be helpful here. So H, P, no, don't have that. IVT, no, don't have I. We could figure it out, but I mean, that would just be an extra step. V squared T over R, that's the one that we want to go for here. So H is equal to 10 volts squared. We're going to multiply that by 60 seconds. and then divide it by our resistance, 20 ohms. Okay, so 100, or 10 squared is 100, 60 divided by 20 is 3, 100 times 3 is going to get us 300 joules of heat being taken out of the circuit. Since it's a light bulb, then it produces 300 joules. Because we use the same variables so often in these equations, there are actually a lot of different ways you could go about doing this. When we set up this equation earlier, it's because we made some different substitutions. You could have gone through and found the current. Maybe you found the power first. It's really open to interpretation here. Whatever you think is the best route, whatever makes the most sense to you, that's the way that you're going to want to do it. Real life application, or I guess they're all real life applications, maybe a little more everyday or commonplace application of this idea of circuits using up some amount of energy would be your family's getting an electric bill every month. So when that electric bill comes, it's not measured in joules. Like you don't, require 500 joules to run your TV for a minute. It's all measured in kilowatt hours. So we use a lot of power, and counting by the joule is just kind of silly. You would have ridiculously huge numbers on every electric bill. So what they do instead is use the kilowatt hour. So a kilowatt hour is a power multiplied by a time, which gives us some total amount of energy. So when your electric company is determining how much to charge you, they measure that power output, so they know how much power they're putting out, and the amount of time that you were using that power. So watts and seconds, like I said before, they're so small, you would get really big numbers. So they use the kilowatt hour. So kilowatt is just 1,000 watts. An hour is 3,600 seconds. So quick calculation here. 1 kilowatt hour. Let's see what that would be in joules. So we have 1,000 watts per kilowatt, and multiply again by 3,600 seconds per hour, and we're looking at 3.6 times 10 to the 6 joules. So in reality, you're using quite a bit of kilowatt hours every month. You could check it out. There's a box on the side of your house that keeps track of how much power you're using. That's actually how the electric company knows. They send someone out every month to check that box and record how much you're using. So, fun little activity. Go see. Hey, why not right now? You're supposed to be at home watching this, right? Go check it out, see what you get. Maybe we'll make a little competition out of it. See who is the most eco-friendly AP2 student out there.